I had a proposal before class to do the following problem. This was not on the homeworks, but it involves, this was on one of the bonus practice problem only homeworks that I announced in class, is not due for credit. But this is one of those questions that involves all of the skills that we've been practicing, and you should know each of these steps. We're going to practice going through this step by freaking step, one puzzle piece at a time. So here we go. I drag a box which is dragging a box which is dragging a box. I pull with a tension on one rope. Let's call this rope A, this rope B, and this rope C. The masses of the boxes are, the first one is 3 in line, second one is 5 in line, and the tail of the caboose is 2 kilograms at the end. Your task is to find every force on every box and find the acceleration of the system. You could find these numerically. Around G to 10 for around G to 10 for the purposes of getting consistent answers. And I want you to step through this sequentially like we just did. Here's our goal, but I think we should break this into pieces. I'm going to answer pieces, one step at a time. Your first goal, what you need to have done in the next few minutes before I talk again, is decide for each object what exerts a force on said object and draw those forces on a free body diagram, on a force diagram. Again, for consistency, call this rope C, this rope B, this rope A, and let's call the boxes by their mass. The box 2, box 5, box 3, yeah? Straightforward? Okay. Find the forces acting on each box and draw them on a force diagram. We'll start there. Ready, set, go. You may work with partners. No friction. If there were friction, I'd have told you. Yeah, you're right. F for floor. Oh. Call the thing that's touching floor, F for floor. Oh, F. That sounds like force. How about T for table? No, T sounds like tension. Oh, crap. G for ground, lowercase g, uppercase G, so that he doesn't get confused with 9.8 or 10. There, G for ground. Don't put this in Google form yet, by the way. I didn't ask you a Google form question. So for number 2, the bottom part of diagram. Hey, 1 minute, I've gotten this far. Gesundheit. Okay, time's up. Hopefully everyone has force diagrams. Now I can't go around the room and look at all your force diagrams, so let me spot check you on the various puzzle pieces here. Incidentally, the questions I'm about to ask are totally typical exam problems for for those extra questions to test on the skills that I said haven't been on the homeworks. That we spent much like class time on, but I haven't found questions to do. Okay, so example question uno. List every object acting on the 2 kilo box. List every object acting on the 2 kilo box. On the Google form, question A, every object acting on the 2 kilo box. Yep, one letter like we've been practicing, like I've been instructing. Not the force. I just want the object. The letter for the object. Okay, 10 seconds. Time's up. We have 33 incorrect answers. Let's go through our process for how to identify what exerts forces. Part uno, what's the first thing to check each time? What did I say 4 weeks ago about how to identify what exerts a force? Number one is there a planet nearby? This is not specifically stated to be acting in deep space. So what object should you always include in any problem that doesn't specifically state that? Earth, E. Now we draw a little box around the object. And we identify if it passes through the dotted line, what can we do? Include a force. Does box 5 touch box 3? Is box 5 crossing that dotted line? Is box 5 exerting a force on the 2 kilo box? No. Is string A exerting a force on the 2 kilo box? No. What's exerting a force on the 2 kilo box passing through the line? It's rope C and ground G. The correct answer is C, E, G. Okay. That was 2/3 of you got it. But I really think that we could do better than that. Why don't you take a minute, Google question B, and revisit the 5 kilo box? Incidentally, you should amend your answer, your free body diagram. If your free body diagram was missing some interactions, you need to include that. I'd really like to see more than 65% of y'all getting this next one. Google question B, list all of the objects interacting with the 5 kilo box. That's more like it. Oh my God, please follow freaking instructions though. Am I asking for types of forces? Am I asking for the triplet notation? I am asking for what? The objects. I've given you names, 2C, 5B, 3AG, and obviously Earth. You are listing those letters. Okay, that's more like it. We're now at 90% correct. I think we can still do better than that, but I'll take this for starters. Correct answers are there's a planet nearby. E should be in your list. Now I draw a dotted line around, and the things that pass through the dotted line are the ground touches, rope B, and rope C touch. So the correct answer, I would say, is B, C, E, G. Most of you got that. No, vast majority got that. One more time, though. Google question C, what objects interact with box 3 kilogram? Box 3. Google question C. Please use the letters indicated. Don't make up your own. Okay, we're at 98% correct. Let's list this. Is there a planet? E, yes. Is there a string on the right? A, yes. Is there a ground on the bottom? G, yes. The one thing that a couple of you forgot is that string B is also passing through the dotted line. B also acts on the object, on the 3 kilo object. Okay. The next thing that I would like to check is let's check the directions for some of these forces. I don't want to do all of them. Let's check the directions for each of the forces on the 5 kilo box real fast. So I just want pluses and minuses. The forces that we found are the force exerted by B, the force exerted by C, the force exerted by Earth, the force exerted by G. So give me 4 plus or minus signs corresponding to the up, down, left, right for B, for C, for E, and for G in that order, okay? So I want you to consider the box 5 and tell me the up, down, or left, right for each of these. This is Google Form D. That's right. Everything in one. Just 4 symbols. Each symbol is a plus or minus. This is all in D. There should be 4 symbols. There are 4 symbols. Oh, wait. Those just ran together. Okay. No, y'all did it right. Not all. Okay, 1 minute. 30 seconds. Chop chop. Hmm. 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 And we're back down to only 3/4 of y'all. Okay, let's talk about these each one at a time. How do we see the direction of gravity? Which direction does Earth weight force things? Down. Earth exerts a downward force, which I'm going to say is a negative force. The normal force is not always up, but it is always directly out of a surface, perpendicular to the surface. That's the meaning of the word normal to a math or physics person. Normal, right angle. So if I've got a horizontal surface, there is a vertical force, upward force. That is right angles to the surface. Vertical is right angles to horizontal, and it is out of the surface. So the normal force that the ground exerts is in the positive direction. Now let's talk about the horizontal forces. You can tell the direction a force acts on the object by a tension acts on the object acts on an object with by looking at which way a rope goes. If I've got a rope pulling me up, if I've got a rope leading from my head, it is very difficult for that rope to push down on me, right? If you try to take a rope and push with it, it doesn't work so well. So ropes exert forces in the direction that the rope goes. Which direction is rope B leading from the 5 kilo object? He's on the right side of the box. It exerts a rightward force. Which direction is box C, rope C attached to the 5 kilo box? It's on the left side of the box. So the correct answers are plus, minus, minus, plus. There were a lot of different wrong answers for this one. Question, please. Normal force is always by definition at right angles to the surface. So if I've got a horizontal surface, it's got to be either up or down. It's got to be vertical. Then we think, does the ground suck us downward? Or does the ground support us pushing upward? You can say it always, normal force pushes away from the surface.
Negative, then 5 would be beneath G.
5 would be beneath G. What?
Like the box would be beneath the ground technically.
Or if you've got something sitting on top of the box, that pushes away from that something. There was a Google question, or a chat, online question. I asked, we don't look at the leading arrow showing right, we look at the position of the rope. I was asking about the 5 kilo box. The 5 kilogram box does not touch the rope on the right. Box 5 touches ropes B and C. A has nothing to do with the 5 kilo box. The other follow-up to that is box A is getting pulled with a tension A on 3, tension of A on 3, and I did indicate that that rope is pulling to the right. But that is applicable if I talk about the 3 kilogram boxes forces. Okay, I wish to repeat, let us do for the 2 kilogram box. Y'all, most of you told me that there are 3 things acting on this box. There is rope C, there is earth E, there is ground G. Google question E for evil, or easy, depending on how you're doing. List the plus minus signs for this. Gesundheit. Okay, time's up. Better. The only goof here is a fair number of people said that C points left. If the rope is on the right side of C, to say that the force is left is saying that the box which is leading away from C is pushing the box right. Does it feel reasonable that a box on the right side of the rope, a rope on the right side of the box is pushing that box backwards? I hope you would agree that no, ropes don't push. A rope on the right side of the box pulls the box to the right. It does not push the box to the left. I do want to emphasize something, by the way. Rope C is on the right side of the 2 and on the left side of the 5. It means it does exert a different direction force on the 2 than on the 5. You cannot memorize just C always goes left. If that's what you were thinking, hey, I've already found C, you have to consider on what object are we going? There is no such thing as the force of an object is always left. It's not true. Okay, now I want to test to see if you remember triplet notation. Let's say for the let's do the 3 kilo object. The 3 kilo object, there are 4 objects interacting. I want to hear the triplet notation in the following order. The force exerted by object A, the force exerted by object B, the force exerted by the earth, and the force exerted by the ground. Give me the triplets. Each triplet is separated by a comma. The triplet for A, comma, the triplet for B, comma, the triplet for E, comma, the triplet for G, yeah? 3. So this is Google question F. Show me that you remember the force notation that we've been practicing. Triplets, not type, triplets, not signs, triplets, the force 3 letters that we have been practicing. And I would like it in the following order: the force exerted by A, then B, then E, then G. Always correct, Marcus. Always the kind dealer feeler. Again, the box, call the box without loss of generality, 3. Like I said at the beginning. And we're going to call the ropes what's listed in the diagram, not R. Okay. So again, I've got 4/5 of you. I would like more. So, what did I say the letter for the dealer for rope A is? Did I say R? No, I said A. A is the object exerting a force on the 3 kilo box. Most of you remembered that the 3 kilo box is called 3. The third letter in a row is always the object under study. So the third letter should be 3. Should it be B? No, it should be the 3 kilo box because I specifically said it's 3. Now let's talk about the kind of force. This I was very pleased to see. Almost everybody remember that planets exert weight forces. The ground exerts a normal force. I did have a couple of mess ups on what kind of force ropes exert. Go back to lecture 1 in the force land. Ropes, chains, strings, cords exert tension forces. Most people got that part though. And most of the goofs here, of the 20% goofing, we're not listening to the names, we're not reading the names that are given, okay? So let's go from here into practicing writing net. No, wait, I will fill in my free body diagram here because I want I want you to check yourself. I can't check you on the Google Sheet, but I can ask you, I can beg you to check yourself and ask if you've got a problem here. This is the tension of C on 2. This is the weight of Earth on 2. This is the normal force of ground on 2. This is the tension force of B on 5. The tension force of C on 5, TC5, is the weight force of Earth on 5. This is the normal force of ground on 5. The normal force of ground on 3. The weight force of Earth on 3. The tension force of rope A on 3. And the tension force of B on 3. Take a quick look. Your diagrams should be identical, letter by letter. Yes, I am testing on this. Not this Google Sheet, not your papers right now, but this will be on. You must be able to do these skills that we've been practicing. And if you've got one missing, Nadia? Nimals? Nimans? Nobody? No questions? Question me. Uh-huh. There better be movement. What is pulling backwards? There's no friction opposing the motion. Consider box C, box 2. There's no leftward force. It has to accelerate right. You got a toy train system. You pull the toy trains along in a row. They have to move along with you. You better believe there's acceleration. And we'll prove that in a minute. We'll solve for the forces numerically. Okay, I would like you to show me that you can write a net force expression. Let's look at the vertical direction for the 2 kilo box. Google question G is just write an algebraic expression using the letters provided, the force names provided, to tell me what the total force in the vertical direction of box 2 is. Do not write an equation. Yes, F does equal ma, but that's not what I'm asking for. I want you to show me that you can add. I want you to show me that you can add. Again, Google question G is write what you would have for the net force on object 2. Do not write Newton's law. Do not write Newton's law. I do not want an equal sign. I do not want a list of forces. I want you to use the letters given in the vertical direction, not the letters, the forces given to write a net force expression. Show me that you can add up forces on an object. And this is Google question G. G for golf. One more time, I am not asking for an equal sign. I am asking for an algebraic expression. An equation has an equal sign. I'm not looking for an equal sign. I'm looking for the left-hand side of Newton's law. For the 2-kilogram box, not the 5-kilogram box. Again, you must use the letters, the names provided. These are no longer object names. These are no longer single letters. I want it written in terms of the force letters that we've provided. I am not asking for numbers, my friends. Vertical direction. Don't tell me horizontal. Tell me vertical. Okay, give it your best shot. Last chance to enter. And I'm grading to see what next happens. Okay, so I've got a third of the class either not following directions as provided or adding incorrectly. This should not be the hard part. Let's review how to add things together. Is tension acting up, down? This is the vertical direction. Which way is tension? You should not write T in your vertical net force equation. Look at what goes up, down. There should only be an N and a W in this. Also, which object did I say? I said the 2. I had a fair number of people tell me for the 3 and the 5. Okay. The last question is which direction is normal force, up or down? And what sign do I give for up forces? What direction is W force? And what sign do I give to downward? The last question is, what specifically did I say multiple times for the format to write these in? Did I say N minus W, single letters? No, I said use the names provided. The correct answer for question G was NG2 minus WE2. That is the net force on the 2 kilogram object. In the vertical direction, I should be precise. Question. Arithmetically, 1 minus 2 and negative 2 plus 1 are the same number. You may always write addition and multiplication and stuff in any order by the associative law of arithmetic. Associative? Yeah, I think. Right. Okay, so, no, commutative. Okay, whatever. So the last step, no, I still have a third of the class missing this. Let's do another example. Tell me the horizontal net force expression using the letters given on the 3 kilogram box. Horizontal net force on the 3 kilogram box. Do not write an equation. Do not write equals MA. Write the total force expression, just like we just did here on the 2 kilo vertical, right? The 3 kilogram horizontal, okay? This is Google question H. Which direction did I just say? Horizontal. Don't tell me about normal and weight, please. Please check your neighbor to see which box they are analyzing. I have a fair number of people, for whatever reason, who are analyzing a different box. Okay, time's up. Were we talking about box 5? The correct answer is we are analyzing box 3, so you should not use these forces. You should use the forces that I said and circled. The correct answer for box 3s involve tension of A on 3, tension of B on 3. Which direction is A pulling? Look at the arrow. Which direction is B pulling? There is the net force expression that I was looking for. The correct answer is TA3 minus TB3 for Google question H. Adding forces, making a net force expression, is as simple as looking in a direction and putting minus signs on the downs and lefts. That's all there is to it. And listening to what problem I'm talking about. Okay. So now let's apply this. Let's apply Newton's laws. I want you to write Newton's second law. That's the equation one for box 5. You need to plug in what the net force is. The algebraic expression for net force in terms of what is given. So again, for Google question I for I for iota, I for India. I want you to tell me the net force on box 5 equals the mass of box 5, Newton's second law. Again, we are talking about which direction? Horizontal forces. Okay, my friends, we already have 20% not answering the question asked. What's Newton's second law? F net equals mass times acceleration of that object. I have a number of people not telling me that equation with things plugged in. They're simply telling me the net force expression, repeating what we did in the previous example. I also have a fair number of people talking about the vertical direction. Which direction did I ask about? Tell me the horizontal, apply what you now should know, but the horizontal direction applying Newton's second law. Plug in Fnet, plug in M. Do you know A? And you know M, by the way. You may plug in what M is equal to. Okay, 1 minute. All righty. So the problems here that I am seeing, let's address these one by one. A number of people are assuming that the box is not accelerating horizontally. What did I say to him 2 minutes ago? You've got to chain of blocks and you pull him right, is he going to accelerate? Yes, there's no friction force opposing this motion. You apply an external force to a system to the right, and there's nothing opposing that to the left. It has to accelerate. A is not zero. It is not stuck in place. There's nothing to keep it stuck in place. Part 2, a number of people said that A is negative G. When is A always equal to negative G? In free fall. Is this in free fall? No, do not assume that A always equals negative G. A equals negative G when you are freely falling. I had a couple people tell me about normal and weight. That's the vertical up-down direction, not the horizontal left-right direction. And then the last big thing I saw is that a large number of people told me the net force equals TB5 minus TC5. That's what net force is, but I didn't ask you to give me an algebraic expression for net force. I asked you to apply Newton's second law. Again, Newton's second law is the equation one. The net force on an object is equal to the mass of that object times the acceleration of that object. TB5 minus TC5. You know the mass of the 5 kilogram object. He's 5 kilograms. You don't know the acceleration of the object. We leave it as a letter. Correct answer was TB5 minus TC5 equals 5A. Bang. Let's try this again. Hell, do it for the 2 kilo box. Yes, question first, Mitzi. You could. You could. Algebraic rearrangements are always permitted. A over B equals C, A equals CB, either way. But a quarter of the class wasn't answering that. Okay, again, do the horizontal direction, apply Newton's second law to box 2. Are we analyzing box 5? Which box are we analyzing? 2. What's the mass of box 2? Is the mass of box 2 3? This is Google Form J. Horizontal. Okay, time's up. Got 90% of you. Okay. 5 of you told me about box 5. I didn't ask about box 5. A couple of you told me about the vertical direction. Didn't ask for that. I asked for the horizontal Newton's second law for box 2. There is only one force acting horizontally. It's TC2. What is the mass of box 2? Is it 3? What is the net force equal to? Is it m divided by a? F equals m times a. If you want to solve for a, you can get a fraction, but f does not equal m over a. F equals m times a. Okay, so so far I have two equations. I would really like more people to get this. Let's apply this one more time. It's the same pattern. We're doing the same thing. Horizontal, box 3. All right? Tell me about these forces. Newton's second law. This is Google form K. I'm looking for an equation now. There should be an equal sign in your answer. And MA should be on the right side where you have plugged in what you know about M. Again, the question is horizontal net force equals MA on box 3. Okay, time's up. Is acceleration 10? How do you know acceleration isn't 10? Because I said so. Acceleration 9.810 applies in free fall. You cannot just assume that we are in free fall. We are not freely falling. We have not solved for acceleration yet. Maybe acceleration equals 10, but we're not there yet. We haven't done that. You can't jump to that. What is the rightward force? Is it A or B pulling right? A is pulling right. So the sign for A should be plus or minus? The sign for A should be plus. The sign for B should be minus. The correct answer is TA3 minus TB3 equals 3A. You could also plug in, you know what TA3 is actually. I gave that to you in the problem statement. So it is also perfectly acceptable to write 100 minus TB3 equals 3A. Oh wait, acceleration does equal 10, but you shouldn't have jumped to that yet. We'll prove that in a second. Okay, we've got 3 equations and lots of unknowns. Properly, I should have said acceleration 2, acceleration 5, acceleration 3. Why didn't I? There's logic and reasoning here. How come I didn't say separate accelerations? They're all the same system. How do I know that all the boxes accelerate at the same rate, though? You can have a system where the two parts, if you get a spring, they won't necessarily move together. It's not time. It's not friction. They're connected to each other by something that don't stretch. If this string, if string C is stretchy, then the position of 2 and 5, the distance between them might change. The velocities might be different. The accelerations might be different. As long as string C is not stretchy, which we're assuming when talking about tension here, we haven't done springs yet, then wherever box 5 is, box 2 is the same distance behind it as there was before. If box 5 is moving at 5 meters per second, box 2 had better darn well be moving at 5 meters per second. So if you have stretchless string, which you should assume at this point in the semester, if you have stretchless string, the accelerations are the same. Question, thought? No, yeah, please. Because that was provided for TA3. Right there. If you wrote TA3 minus TB3, that's fine too. Okay, so one of the things that is being applied here is that they aren't three different accelerations, A2, A3, A5. There's one acceleration for all the boxes. They're all moving together. There's another piece of wisdom here that I can use to reduce the variables. Can you tell me about the nature of tension? What is true about the tension of a rope? What did I teach you about tension? What have we been doing with tension on one side versus the other side, for instance? If a rope has a tension of 100 newtons this way, how hard is the other side? Same. So the tension that rope C is exerting on 2 is identical to the tension that rope C is exerting on 5. It's the tension in the rope. It's how hard that rope is pulling on both ends. Do you remember having done this? I didn't make a big deal about this. We can actually prove this using Newton's laws separately. I'm just going to leave this aside and say that here's a thing to know for now. Ropes pull equally hard on both sides. We call that force the tension. Okay, so if TC2 is TC5 and TB3 equals TB5, I'm going to remove the second subscript because it doesn't matter which object each of these tensions is acting on. Okay, I don't always want you to do this, but we're going to do this now because we've reached the point where we can solve algebraically for stuff. I have 3 equations. I don't know B, I don't know C, I don't know A, but you can algebraically combine these equations with the principle of substitution and get one master equation and solve for A. Practice your algebra. The hint is plug this in for C, solve this for B, plug this in for B, and algebraically solve. Find acceleration. Find the acceleration in box L. See who's able to algebra. Again, the hint is get rid of this tension here by substitution. Solve for B, get rid of this B here by substitution. Solve for A, then you'll just have A as numbers. Oh, good so far. I'm not looking for an algebraic expression now. I'm looking for a number. You can solve for A. It gives a number. If your algebra is weak, take it step by step. You must do the same thing to both sides in algebra for every single step. Again, the hint is solve equations that have one tension in them for the tension, then plug into the middle equation. I think is the smoothest way to do this. What are the units of acceleration, by the way? Meters per second squared, not meters per second. We're not finding a velocity. This is Google question L. Please put this in L. Okay, we need practice here. You need practice here. Many people need practice here. Let me walk you through how to algebra here. Here's how to algebra. If you know what TC is equal, if you know what TC is, if you know what TC is equal to, instead of writing TC, you can write 2A. If you could solve this for TB, instead of writing TB here, you can write what TB is equal to. So to do this, well, let's see, I don't have TB on the left side of the third equation. Let's solve for him. I add TB to both sides to get rid of the minus sign. And I'm going to subtract the 3A from both sides to get it away from TB. You could also subtract 100 from both sides and then flip both sides as signs. Either way is fine. Okay, I know what TC is, and I know what TB is. So I'm going to take these and plug them in. TB, 100 minus 3A minus 2A equals 5A. I'm just combining the equations with the algebraic principle of substitution. Now, how do I get the 3A and the 2A away? I add 3A and I add 2A to both sides. I get 100 equals 5A plus 3A plus 2A. And how do I combine when I add terms? I can factor out the A here and say this is equal to 5 plus 3 plus 2 all times A. And what I said before was actually the person who jumped ahead and said A is 10 was correct. 5 plus 3 plus 2 is 10. So I could divide both sides by 10 and I get A is 10 meters per second squared. You now have the acceleration. You can go back and plug it into the equations that you've had before and find the values of the tensions. We've got a minute left. You could do it. Tell me the acceleration of B. Gosh darn it. The tension in rope B. Use the acceleration we just found, plug and shove, evaluate tension B. Okay, good. More people are getting this right. I've got the expression TB equals 100 minus 3A. If I plug in A equals 10, 100 minus 3 times 10 is 70 newtons. The tension in row B is 70. If you're missing these questions in the last bit, I strongly encourage you to go practice some algebra. You can drill and kill it on freaking Khan Academy. I don't recommend Khan Academy for much, but here's the thing I do recommend it for. Solve equations, be able to plug in. It will greatly help you. Anyway, I will see you next time with a midterm. Adios.